Hello. In this session of isomerism, we look at stereoisomerism. We have said initially, stereoisomerism is manifest in two forms as either geometric isomerism or optical isomerism. Let's take a look. To begin with, we are going to look at geometric isomerism, and in geometric isomerism, we agree that it is the existence of differing structures in respect to orientation of foreign molecules. Foreign molecules in high carbon are basically any species apart from carbon, hydrogen, or oxygen which is attached to the chain. Let's take a typical example of 2,3-dibromobutane. 2,3-dibromobutane may be represented by a chain of 4 carbon atoms, and the bromide molecules in positions 2 and 3 respectively, as inferred by the name. The next is the arrangement of hydrogens, which follows the carbon rule of 4 bonds round each carbon. And in this respect, that would be the arrangement of the molecule. Now, the principal view here is that the bromine molecules are on both sides of the symmetry to the structure. In this case, they are on one side, so the name is cis 1, cis 2, 3 dibromobutane. What if we rearrange the structure such that the bromide molecules are not on the same side of symmetry? What will happen is that we would have bromine on one side and bromine on the other side, and following the carbon rule, the structure would look as what we are completing here. In this present case, with a clear view, we have the bromide molecules on opposite sides. Now, since they are on opposite sides, the name of the species will remain the same, but it would be a trans molecule. So we name it a trans 2,3-dibromo because there are 2 butane. And therefore, we could say that geometric isomerism is the differential arrangement of foreign molecules in a displayed structure, in which when the displayed structure shows the foreign molecules on the same side, it is a cis molecule, and when it shows the foreign molecules on opposite sides, it's a trans molecule. This could also be referred to as the isomerism and antigen molecules. Now, isomerism will stand for the cis, and antigen will stand for the trans molecule. Those are German descriptive nomenclature. Therefore, in summary, the geometric isomers differ in respect to arrangement of position of foreign molecules. When they are on the same side, they are known as the isomer or the cis structural isomer, and when they are on opposite side, they are the antigen geometric isomers or the trans. Next, we have the optical isomers, and the term optical means involving photo or mirror images. Therefore, optical isomers differ in respect to the orientation of the mirror images. For example, the optical isomers of tetraamine cuprate complex molecule. The tetraamine cuprate complex molecule will exist with a mirror in between them, and we will represent copper as a chiral center, chiral in the sense that it's surrounded by other molecules, and these molecules may be displayed in varied orientations as shown there. These molecules are normally ligands like hydroxyls, which provide a pair of electrons. So, assuming that it is tetraamine, which means there are 4 amide species attached in their respective positions, and and I could see that they are in polar orientations. Remember, amides come from ammonia. So there are 4 amide molecules, and there are 2 hydroxyl molecules. Each are electron donating species known as ligands. And the species in the middle is a chiral center, in this case copper. Now, when you put the second copper on the opposite side of the mirror line, the sequence is the same. We will have the arrangement of the amides in polar orientations, but as mirror images. And in this respect, we will have our H2N. Again, we will have our H2N. Again, we will have our good NH2. And then we will have our NH2, another NH2, and then we have the OH becoming HO, another OH becoming HO. So in that respective arrangement, you can clearly see that the amides are in positions which are mirror images. They are non-superimposable. I'll use the illustration of my palms. An attempt to bring the hands together, and we find that they are non-superimposable because the thumbs are on opposite orientations. However, when we clap our hands, there is a superimposition, thumb to thumb, pointing finger to pointing finger, middle finger to middle finger, wedding finger to wedding finger, and little finger to little finger. So that represents superimposable. However, we are saying that optical isomers are non-superimposable mirror images, which means they do not overlap. And these non-superimposable mirror images are referred to collectively as enantiomers. Now, enantiomers are of 2 main forms. We have the sinister or the S enantiomer and the rectus or the R enantiomer. The sinister is on the left-hand side and the rectus on the right-hand side. This is a clear display of what we are calling optical isomerism. What then have we studied here? In this section, we have looked at what is known as sterioisomerism. And we have seen that in sterioisomerism, there are 2 forms of isomers, namely geometric isomers and optical isomers. The geometric isomers that we have evaluated have brought a clear distinction in terms of orientation of foreign molecules, where we have said that when the foreign molecules are on the same side, they form cis isomers exclusively. When, however, the foreign molecules are on opposite side of the center, they form trans molecules. And when we look at the second form, which is the optical isomers, we've said they are non-superimposable mirror images known as enantiomers, with the rectus molecule on the right and the sinister molecule on the left-hand side. The terms rectus and sinister are Latin terms used to describe the procedure of arrangement. And in this case, therefore, we can say comfortably that isomerism is the existence of different structures of the same molecule, normally exhibited by organic compounds. In isomerism, there are 2 principal forms of isomerism, namely structural isomerism and stereoisomerism. In structural isomerism, there is a range of 3 different forms, namely the chain isomers, which differ in respect to position of carbons, the positional isomers, which differ in respect to the position of the functional group, and the functional group isomers, which differ in respect to the nature of the family formed by the arrangement of carbons. The stereoisomers, we can conclusively say, are of two main forms. They could be either geometric isomers, which differ in respect to position and arrangement of foreign molecules as cis on the same side or trans on opposite sides. And two, that the stereoisomers may be optical in form, which are non-superimposable mirror images known as enantiomers, with the rectus molecule on the right and the sinister molecule on the left. Thank you very much. That has been a description of the different forms of isomerism.